My name's Andrew Davison and I'm a Professor of Robot Vision here in the Department of Computing. I'm also the Director of the Dyson Robotics Lab, and what my research is mainly about is robotics for home applications. So this is one of the things that I've worked on in the past, which is the Dyson 360i robot vacuum cleaner. And we worked on the vision system that enables this robot to automatically navigate around a home. So what I'm going to talk about today is something related but a little bit different. It's the interesting question of what do you do if you have a large number of robots that want to move around and coordinate to work together in a space. So imagine a situation in the future where we have a team of robots that we want to collaborate together to achieve some useful job. So this could be something indoors, it could be something like a factory, it could even be outdoors, something like a smart farm of the future. So how are all these robots going to coordinate and do a job together without getting in each other's way while knowing where everyone is and what everyone's job is, for instance? So one possibility is that all of those robots could access some central computer which would control all of them. That might be a good solution, but what we've been investigating is an alternative where those robots could coordinate in a purely decentralized manner based on peer-to-peer communication, such that every robot only needs to talk to its neighbours and exchange information with them. The particular problem we've been looking at is how does a set of robots that are working together estimate their locations? So we call this distributed localization. So when we have a set of robots in a space making observations of each other, we represent the problem mathematically as a probabilistic graph. So what we're looking at here, imagine each one of these dots is a robot, and then these lines between them are representing observations that they've made of each other. Now, we want to take advantage of all of these observations to get the most accurate possible estimate of where all the robots are. But we're going to be using a method that solves that in a distributed way using an algorithm called Gaussian belief propagation. So when I click on one of these points here, it's like that robot sending a message to its neighbours, telling it about where it is and the observations it's made of them. And you'll see that as we iterate this, so as I make multiple clicks here, each of these robots sends more and more messages to its neighbours. We'll see that this gradually converges. If I just do a couple more iterations here where everyone sends a message to each other, you'll see that we converge now to very accurate estimates of where all the robots are based on this purely peer-to-peer communication. So I'm going to show you now a simulation of our system called Robot Web for multi-robot localization. So we've got a simulation here of 30 robots that are all trying to drive around this arena in perfect circles of different radii. So there are some beacons, like known landmarks in the corners here, that the robots can observe. But because the robots have limited range sensors, some of the ones in the middle never actually see the ones in the corners. So if I just run this, you'll see the robots driving around and keeping nice circular paths. So if I reveal a bit what's going on here, so this is actually the pattern of measurements that the robots are making. So you'll see that the ones on the outside do go close to the landmarks in the corners and get measurements of those. The ones in the middle though only ever observe each other, but this message passing method allows all of them to have a good estimate of where they are, despite the fact that most of them are really only seeing each other. So just for comparison, I'll show you what happens if the robots don't make measurements of each other. So if I set the sensor range here to 0, you'll see now that we're showing for every robot the actual position that the robot's in and the position that it thinks they're in, and you'll see that these have quickly diverged because the robots are now not making measurements of each other. Thanks for watching. We're excited to keep working in this direction and hopefully to also test it out on some real robots soon. We think this could actually open up much more low-cost and practical robot systems in the future. And for more information and details about our research group and the people that I've worked on with this, please see the links in the description to the video.